Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh and a very good day. We shall continue on our topic for the air breathing engine course. The topic for today is gas turbine cycle for aircraft propulsion, which is thrust augmentation. As all of you have known that we have already gone through the topic on gas turbine cycles for aircraft propulsion, which include the subtopic of criteria of performance, intake and propelling nozzle efficiencies, simple turbojet cycle, the turbofan engine, the turboprop engine, and the final subtopic for this particular topic is thrust augmentation. In terms of the learning outcomes, at the end of this session, you should be able to describe the thrust augmentation phenomena, discuss the effect of thrust augmentation on specific fuel consumption, and finally explain the thrust augmentation in gas turbine engine. Let us go through the discussion on thrust augmentation. If the thrust of an engine must be increased above the original design, so imagine you are having an engine that would like to be operated above the original design value. Several alternatives are available. The first one, basically to increase turbine inlet temperature. For example, it will increase the specific thrust, or known as FS, and hence the thrust for a given engine size. Alternatively, the mass flow through the engine could be increased. So imagine that you have a larger mass flow. Without altering the cycle parameters, both methods imply some redesign of the engine, and either or both may be used to upgrade an existing engine. Frequently, however, there will be a requirement for a temporary increase in thrust. For example, for takeoff condition, acceleration from subsonic to supersonic speed, or during combat maneuvers, the problem then becomes one of thrust augmentation. Numerous schemes for thrust augmentation have been proposed, but the two methods most widely used are liquid injection. So we have the first one as liquid injection, and the second one is the afterburning or reheat. In terms of the liquid injection, it is primarily useful for increasing takeoff thrust. Substantial quantities of liquid are required, but if the liquid is consumed during takeoff and initial climb, the weight penalty is not significant. By having spraying of water into the compressor inlet causes evaporation. So you have a problem of evaporation of the water droplets, which resulting in extraction of heat from the air. So this will affect equivalent to a drop in compressor inlet temperature. Reducing the temperature at entry of a turbojet will increase the thrust. So the thrust will increase owing to the increase in pressure ratio and mass flow resulting from the effective increase in rotational speed. In practice, a mixture of water and methanol is used. So you have a mixture of water and methanol, where the methanol lowers the freezing point of water, and in addition, it will burn when it reaches the combustion chamber. Liquid is sometimes injected directly into the combustion chamber. The resulting, what we call it as blockage, forces the compressor to operate at a much higher pressure ratio causing the thrust to increase. In both cases, the mass of liquid injected adds to the useful mass flow, but this is a secondary effect. Liquid injection is now seldom used in aircraft engine. In this particular figure, figure 3.8, which we have shown to you before in terms of the propelling nozzle system, afterburning, as the name implies, involves burning additional fuel in the jet pipe, as shown here. So we have the hot air coming out from the turbine stages. Okay, and then we have the jet pipe where we introduce the afterburner fuel system to further ignite the hot flow gases, and it produces more thrust coming out from the exit of the nozzle. In the absence of highly stressed rotating blades, because we do not have turbine in the nozzle where we introduce the fuel, the temperature allowable following afterburning is much higher than the turbine inlet temperature. Stoichiometric combustion is desirable for maximum thrust augmentation, and final temperatures of around 2000 Kelvin are possible. This particular figure shows the TS diagram for a simple turbojet with an addition of afterburning to 2000 Kelvin. So cycle of turbojet with afterburning. So we have the ordinary cycle of TS diagram, but in this particular moment, we increase further. Okay, so you imagine this is the initial cycle, and now we have the second stage here where we have the afterburning. This is the portion where we increase further the temperature of the combustion in the nozzle section. Let us go through the discussion about it. The large increase in fuel required is evident from the relative temperature rises in the combustion chamber as well as in the afterburner. However, there is a penalty increase in specific fuel consumption. Assuming that a choke conversion nozzle is used, the jet velocity will correspond to the sonic velocity at the appropriate temperature in the plane of the nozzle. In other words, T7 or T5, depending on whether the engine is operated with or without the afterburning. Thus, the jet velocity can be found from this expression, where Tc given by either TO6 over Tc equal to the gamma plus 1 over 2, or TO4 over Tc equal to gamma plus 1 over 2. So it follows that the jet velocity is proportional to the square root of the T0 at inlet to the propelling nozzle, and that the gross momentum thrust relative to that of the simple turbojet will be increased in the ratio of the square root of TO6 over TO4. For the temperature shown in the figure 3.28, this amounts to 2000 Kelvin over 959 square root, or you will get it to be 1.44. As an approximation, the increase in fuel would be in the ratio of 2000 minus 959 plus 1200 minus 565 with afterburning, to a value of without afterburning of 2.64. Thus, a 44% increase in thrust is obtained at the expense of 164 increase in the fuel flow. Right? You have a 44% increase in thrust, but bear in mind that you spend more fuel. And clearly, afterburning should be used only for short period. This might be the thrust augmentation under takeoff conditions, where the gross thrust is equal to the net thrust. At much higher forward speed, however, the gain is much greater and is often well above 100%. This is because for a fixed momentum drag, an increase in gross thrust represents a considerably greater increase in the net thrust. In terms of another example, the Concorde. So this is a picture of the Concorde flying, made use of afterburning. We know that Concorde use afterburning engine for transonic acceleration from Mach 0.9 to Mach 1.4. The significant increase in the net thrust provided fast acceleration through the high drag regime near Mach 1, which resulting in a reduction in fuel consumption despite the short-term increase in the fuel flow. The afterburnings offers even greater gains for low bypass ratio turbofans because of the relatively low temperature after mixing of the hot and cold streams and the larger quantities of excess air available for combustion. Military turbofans use afterburning for takeoff as well as in combat maneuvering. It is essential for engines fitted with an afterburner to incorporate a variable aerial nozzle. Okay, so you have a variable aerial nozzle because of the large change in density of the flow approaching the nozzle resulting from the large change in temperature. So there is a large change of density, at the same time a large change in temperature. Afterburning will normally be brought into operation when the engine is running at its maximum rotational speed and corresponding to its maximum unaugmented thrust. The afterburner should be designed so that the engine will continue to operate at the same speed when it is in use, and hence the nozzle must pass the same mass flow. So you have the same mass flow at a much reduced density. So this can be achieved only if a variable nozzle is fitted, permitting a significant increase in nozzle area. Note that the pressure thrust will also be increased owing to the enlarged nozzle area. Because you have a large nozzle area, this has to be taken into account when you want to add up the total thrust for the engine. The pressure loss in the afterburner can be significant. Combustion pressure losses is due to both the fluid friction as well as the momentum changes resulting from the heat addition. In combustion chambers, the former predominates, which is the fluid friction, but in afterburners, the losses due to the momentum changes are much more important. The temperature rise is determined by the turbine outlet temperature and the fuel to gas ratio in the afterburner. So it depends on the fuel to gas ratio. It's not just depending on the turbine outlet temperature, and also the pressure loss due to the momentum changes. So this pressure loss is found to be a function of both the temperature ratio across the afterburner and the Mach number at the inlet. So these are the two functions that governs to the pressure loss. If the inlet Mach number is too high, heat release can result in the downstream Mach number reaching 1.0, and this places an upper limit on the allowable heat release, and this phenomena is referred as the thermal choking. Okay, we have a new term here which is called the thermal choking. Figure 3.9 shows values of the pressure loss due to momentum changes and emphasizes the need for a low Mach number. Right, so this is a plot of momentum pressure loss against the afterburner temperature ratio between TO6 to TO4. Okay, then and this particular line is the thermal choking limit, and basically the inlet Mach number are given here. Okay, where the afterburner temperature ratio from 1 to 2, okay, you have Mach 0.2, Mach 0.3, Mach 0.35, Mach 0.4, and Mach 0.5. Typically, the exit Mach number from the turbine of a jet engine will be about P01, the inlet pressure, equal to 0.2650 times 1.482, which is equal to 0.393 bar, right? And it is necessary to introduce a diffuser between the turbine and the afterburner, okay, like what we have in figure 3.8 just now, to reduce the Mach number to about 1 bar before introducing the afterburner fuel. Even when not in use, an afterburner incurs some penalty in pressure loss due to the presence of the burners and flame stabilizing devices, because it is there, because it is a mechanical devices that is being attached in the behind the diffuser at the nozzle section. Another disadvantage of this method of thrust augmentation is that the very high jet velocities resulting from a large degree of afterburning result in a noisy exhaust. The afterburning of Olympus engine, which is shown in this particular picture, Rolls-Royce Olympus engine, which was used on the Concorde, provided around 15 to 20% increase in takeoff thrust, resulting in exhaust temperature of around 1400 degrees Kelvin. The increased noise level, though a serious concern, was significantly less than might be expected from experience with military aircraft. It is most unlikely, however, that any future supersonic transport will use afterburning for takeoff, as a prime requirement will be takeoff noise levels comparable with current subsonic aircraft. As mentioned earlier, this will necessitate the development of variable cycle engine. It is of historical interest that Concorde, which was retired in 2003, cruised at Mach 2.05 for over 2 hours on a transatlantic flight without using afterburning, because they use it at the takeoff stage only. This required the use of highly sophisticated variable geometry inlet and a fully variable convergent divergent nozzle. Some modern fighters, such as the F-22, like in this particular picture, Lockheed Martin F-22 Raptor, can operate at supersonic speeds without using afterburning engine. So this is referred to as supercruise, which is somewhat misleading term. Although performance details are classified, estimates of Mach 1.7 for the F-22 and distances of 200 km have been published. At high altitudes, the speed of sound is 295.1 meter per second, so Mach 1.7 is equivalent to 501.7 meter per second. And the time required for 200 km is only 400 seconds. So this is clearly represents a dash capability rather than cruise. Alright then, That's wrap up our topic on the cycle performance for gas turbine engine. And I will be seeing you for more examples for detailed calculation on the jet engine components. Till we meet again, thank you very much and stay safe. Assalamualaikum warahmatullahi ta'ala wabarakatuh. Bye bye for now.